Okay, so this meeting is now on YouTube live streaming. So let me first start with a brief introduction of our speaker today. So Professor Hong Liang received his bachelor degree from Ningbo University in 2006, and then his master's and PhD degrees from Huazhong University of Science and Technology in 2011 and 2015. So then he joined the Department of Physics of Huazhong Dianzi University as a lecturer in 2015, and then was promoted as associate professor in 2017. And his research interest fell into the area of computational fluid dynamics. So many include the Lattice Boltzmann method, multiphase flows, and heat transfer, and interfacial instability, micro-droplet dynamics, also the deep learning method for hydrodynamics. So far, he has published more than 40 journal articles in PRE, physical fluids, and CISC, and also International Journal of Heat and Mass Transfer. And currently, he has more than 1,000 total citations. So today we are very happy to have Dr. Hong Liang to introduce his recent work on the multiphase and Lattice Boltzmann method and its applications. And Dr. Liang, please start your presentation.
Oh, thank you. First, thank you for Professor Zheng Li and also the Xu Huimeng for giving me the chance to introduce my workers. I'm Hong Liang from the Hangzhou Dianzi University. Today's my talk title is the multiphase Lattice Boltzmann method and its applications. My talk includes 3 parts. The first one is the introduction, and the second one is the multiphase Lattice Boltzmann method, a modeling for the two-phase fluids and the solid multiphase fluids. And then we will use the developed Lattice Boltzmann model to simulation the complex fluid systems, mainly including the turbulent interface instabilities and the macro job dynamics. As we all know, the multiphase fluids can be widely found in our daily lives, such as the rain jobs and the lotus leaf self-clean, and also can be found in many scientific and engineering applications, such as the water pollution, the bubble fluids, and also in the enhanced oil equivalent and the as the joblet based microfluidic chips is a very popular research hot. Now, also in the coating, the printing, and the
Dr. Liang, sorry to interrupt. Can you just use the full screen of your slides, and we cannot see the slides is moving.
Can you see?
We can see the PowerPoint window, but it's not a full screen.
Okay. Sorry.
Yeah.
Okay. Can you see this?
This is the PowerPoint.
Can you see the screen?
Are you using a full screen or use this PowerPoint window?
Full screen.
Yeah. Currently, we can only see the PowerPoint window. It's
Okay. Sorry. Can you see the screen? My screen? No.
No, no. You have not shared your screen yet.
Okay. No. I'll share it. I'm not. This is for me. This is the first time use the Zoom, so maybe it's not. I cannot.
Okay, now you are sharing the window, but it's not a full screen. I'm not sure.
Windows.
Yeah, I mean full screen.
Full screen. Okay. Full screen, I cannot find it.
全屏。
Okay, this one.
你可以把你的屏幕弄成全屏吗？
全屏我找。现在可以吗？
现在我们看到的不是全屏，是我们看到的是一个，就是这个 PowerPoint 的一个 window。你是不是有2个屏幕？
现在。
So there is a button at the bottom.
对，我是用那个不是。
There is a button. You see the 50% on the left of the 50%.
Yeah.
You click that.
Now it works.
On the left of the 50%.
Full screen. I have.
可能你需要退出，重新再共享一次。
你
可以共享 window， 你可以共享你的这个屏幕。
So I know. Okay, it's okay.
Okay, let's try. Currently you are not.
It's full screen. Now it's a full screen or not?
No.
Can you see the full screen? No. Okay. What?
第二个就是社会这个screen 里面这些2种。
Okay. Maybe you can use this window to do your. I'm not sure what we cannot see the full screen. I suppose you have 2 windows, right? You are sharing another window.
Okay. Oh, okay. What happens? Sorry for. Wait. 我是用那个网页来分享的，网页版。但是我这里确实是，我确实我在这个我这里是网页是全屏的呀。对，只有一个屏幕。哦 ，sorry。Maybe it's not. I have click for the screen here. Since the
Okay.
Zoom, yes, I have used the internet, internet the version. I have not downloaded the Zoom the software.
So can you send me your slides by email? I can share the screen for you. So maybe it's because if you use this window, we cannot see the slides is moving. As you move your slides, we cannot see which page you are sharing. So maybe you can send me your slides by email so I can share the screen for you. How about this?
Send email. PPT. Send your email the PPT, my PPT.
Yeah, how large is the file? Yeah, maybe you can use this window to do your presentation, but you need to indicate which page you are currently in. Is that okay? You can use the PowerPoint window to do your presentation.
Is this the Windows? Is this the Windows? Is this? Can see it. Sorry, I asked for some helpers.
Okay.
喂，那个穆学伟，你这个网页说我不能全屏分享。
Yeah, Dr. Liang, maybe you can just use this window to do your presentation. If you cannot share by full screen, we can use this window. Hi, Dr. Liang. Hi, Dr. Now, maybe you can just use that shared window to do the presentation. The only thing you need to indicate is which page you are in. Dr. Now, you can just use that window and to do the presentation if we cannot solve this technical issue.
Okay. Sorry. Maybe it does not work. Cannot see the full screen.
Yeah.
Maybe
You can use this window to move on. Okay, just to click the page you are talking. Then I think should be fine.
I continue to talk. Continue to speak. Extend your slides to you.
Yeah, we can see your screen, but it's the PowerPoint window. I think it should be fine if you just click the page you are talking. I think should be fine.
No. I continue to the speaker. Maybe sorry for this. Cannot see the full screen.
It doesn't matter. It doesn't matter. We just use this window to do the presentation. Okay. We don't need to see the full screen. Yeah. I'm asking him to unmute.
Okay. Can you hear me?
Yeah. That's good. Let's
Can
move
you hear me?
on.
Oh, sorry. As well. Sorry for all. It's not my mistake. Due my mistake, I cannot very use the Zoom the software. It's my first time to presenting file for the Zoom. I have not the Zoom the software. The Zoom is very family.
Okay.
With it.
Yeah, Dr. Liang.
Okay, I continue.
Dr. Liang, I have received your slides. Can I share the screen for you? And you just indicate if you want to change the page, you just let me know. I will share the screen for you, okay?
Okay.
Okay, so then.
I have the center.
Okay, I will share the screen so that.
Okay, sorry. Wait for a moment. Okay.
Okay, does this work?
Yes, I can see the work.
Okay, great. Then let's start. So I will go to the
Okay. Next. Okay. Okay. Wait. Yes. Here. Wait. As we all know, the multiphase flows can be found in many scientific and energy applications such as enhanced oil recovery and the job-based microfluid fluid tip chips, and the coating, plating, and the tracked drug deliveries. As we all know, the expander is the basic methods for studying of the multiphase flows, and nowadays with a great advance in the computer technologies, numeric simulation has become a more and more increasing popular methods for studying the multiphase flows. The next. For as in the 2029, the Nobel Prize in Physics has award to the three physicists for their works for understanding the complex systems. In this regard, we can see that the numeric modeling broadens the understanding of a complex fluid systems. Next. From now we can see that the mathematical methods and models for describing the fluid flows at a different. It can be it can include it can be. So can see it from the three different scales. The first one is at the molecular scales, there's the MD dynamic methods, and then the second scale is the macro scales. That's the equation is Navier-Stokes equation, Navier-Stokes equations, and the development numeric method is the computer, the CFD. And there's also one the models between the macro and macro is the kinetic theories such as the Boltzmann equations, and also the development mainly the numeric methods based on the kinetic theories such as the Boltzmann method, SPH, and the GKS and DSMC as and so on. And we can see our work focus on the Boltzmann methods. Next. As we all know, Boltzmann methods can be studies from the Boltzmann equations with the BGK the collision models. It can be written as at least the following equations. Now in practice we should these equations should be described by in the quality, the space, and the time spaces. We use the characteristic long integrals we can obtain these equations, and with the and finally we can obtain the Lattice-Boltzmann equations. This is a very simple evolution equations, and here is the Fi is the distribution functions, and the Gi is the liquidity distribution equations. Here is the C is the speed of the sound. EI is the quality of the quality. Next, we can see that the equilibrium distribution function is used the Maxwell manners can be written as this one, and the macroscopic qualities can be obtained by some distribution functions, and the momentum of the zero momentum of the distribution functions, and the first momentum of the distribution functions, and then the energy can be obtained by the second momentum of the distribution of my functions. Next. Now we can see that the evolution of Lattice-Boltzmann include two stages. The first one is the collisions, and the second one is the streams. And you can see the movings. Next, you can see that this is the movings. And it is the Lattice-Boltzmann is very simple, and if it also can be easy, also can be easier to code, and can be easy to perform on the high level computers. Now next, and we can see that we can nowadays see through different types of the multiphase Lattice-Boltzmann model has been replaced from the different pictures of interactions. The first one, the multiphase Lattice-Boltzmann model is called the color gradient models, and the second one is the pseudo potential or punching models, and the second one is the fluid energy models, and the last one is the phase field based models. Also someone called it the mean field models. As the last one is always the focus. That's the phase field Lattice-Boltzmann models, since it have fair physical foundations for the tracking interface or multiphase flows. Next. As we can know the level, they mainly have two popular phase field equations for interface the curvatures. The first one is the Cannon-Henley equations, and the second one is the Ellicott equations. And as one can see, that's the Ellicott equation actually is the fourth order equations, and the Ellicott equation is the second order equations. In this ground, the Ellicott equations have a lot of equations, such that numerical modeling of these equations have a lot discrepancies. Such in this ground, we will use the Ellicott equation to the modeling interface, and also the phase field equations should be coupled with the Navier-Stokes equations with the surface tension force. Next. LB equations for the Ellicott equations, as we all know, that's the first one for the first equation LB models for the equation is the balance Frank-Henry. In the GCP he present the first models. He defended the equation distribution function as this. In our model, there's no the source terms, so we applying the Chapman-Ensker equation. Now we give another Lattice-Boltzmann equation is we descend the equality distribution function as this one, and also the descend the source term as this one. Now we use applied the triangle analysis. We can find that the model of factor Harry cannot the quality the analytical equation accurately. That include some error terms, and our models can be created require the annual equation accurately. In this in series, we can see that our model can be more accurate than the model of factor Harris. Now we can next. And also in addition to the LB model for the eloquent equations, we also need another LB equations for the solve the Navier-Stokes equations. Inspired by the Gauss force models, we present a very simple LB equation for Navier-Stokes equation with a substantial force. Well, the cubium distribution function can be defined as this one, and also give a very simply the force term can be defined as this one. Interest readers can be found referred to the later papers. Next. We now we use the five benchmark the multiphase the problem to test our model. The first test is the static job, and the second is the Lloyd Poisson flume, and the second is the bubble racing flux, and the second is the Sandel decomposition, and the last one is the job impact on the film. And let's see, that's as we can see that this is the result of a solid and unsolved jobs in the square computers jobs DEMs. As we can see that the obtained interface agree very well with the integer patents. We can also see from the figure B, we can see that the density is agree well with the analytical solutions. Also, our model can be achieve a very low spring velocity with the order of 10 negative nice. Next. Now we can the second test is a Lloyd procedural flux, and this problem described can be as this. It's a pamper. The upper of the pamper is the gas filled with the gas, and the down the pamper is filled with the liquid. And this problem have analytical solutions can be presented as this. As we all know, we can find that the previous estimation of the case are limited to the lower density regions smaller than the 10, and it's difficult to capture the velocity fields and the condition of high demand, density regions with Lattice-Boltzmann methods. And next, since the Lattice-Boltzmann force is diffuse interface methods. From the source, this is also in the picture, in the figures, we can find that our model indeed is accurate than the previous model with the case with different density regions. Our model can accurately capture the velocity profiles, and some division can be obvious opposite in the preference of the Lattice-Boltzmann models. Next. Also, can the theoretical errors of can be accurate and the submarried in this table table 1, and we can see from the table 1 that the present Boltzmann model is more acute than the other model LB models. Next. The third test is the bubble racing flows. We simulate the bubble flows with the dynamic relation of 1,000 cells and the dynamic the first relation of 100, and compared our simulation results with the improved LB, the flux solver, and the advanced level set methods. The base point can be described by the two dimension the parameters, that is the real numbers and real numbers. Next. We can see this result. The upper figure is result by the improved LB flux solves, and the law of this the results by our developed Lattice Boltzmann method. We can see this agreement between them. Next week. Also in this case can be also see lattice agreement between them. Next one. This is the position of the bubble mass centers. We can see that our LB simulation result is also agree with the preface the port. Next. This now we simulation the case the bubble racing in a pattern of the physical parameters. We can call it that has 12 cases. The chaos KAE to chaos A1 to chaos KA6, and the case B1 to the B6. And this the case the case can is agreed with the experiment setups. Now we can see this the simulation result. Next. This we can find that under this case and this simulation conditions, we can find that the bubble can research a state trappers, and we give and capture the state sharper of the bubble and compare with the preference results, including the experiment, the front trunking method, and also the plan for LB simulations. We can find that our LB simulation results can agree with the experiment and the front trunking method, and can be accurate than the place LB simulations. We can see that in these papers of Wang, he has claimed that his model is cannot applied to the case with high density regions. So the result, the principal result is at a medium density regions. Next. We can see this is the case B1 to case B6. We can see that our results also agreed well with the press results in next. So the first test is the speed down the compositions. We can see that at the first time the system is just tubed, and as the time goes on, and the quarter phase separated with the phase of the gas case, and we can see the two phase in the system. So our model can capture this the process of the phase segregation. Next. Next. The last test is the job impact on liquid films, and we can see the result next. Next, we can see we can see this in the job can be impacted the required films with first with the wave number of the and 18,000 and the real number of 500. We can see that with the job can can see the job can be a spread of the quan, and the quan is can be cannot found is decreased with the increase decrease of the real numbers, and next and at a very low real numbers, we cannot see this easily across the phenomena. Also, we take computer spread the radius and the fullness dimension times. We can find that the spread radius of the bubble is this job is agree with the pollen with reported in the paper of the POF. Next. The second work is that we developed robust Boltzmann method for the fluid solid multiphase flows. The idea of this work is a key point of this work is to contribute wetting boundary wetting the boundary conditions. The starting of this work is we from the total number from free energies of two-phase solid systems. We can see that the second one is the present the wall of free energies. The second one is the present is the bubble of free energies. We think the flotation operators to list all the total free energy fractions. We can obtain these equations. Mathematical equations like this. Next. Master in the for the two-phase systems, the energy fluid energy should be to zero, and which can lead us to the equations relations as these ones. And for the confidence of discussions, we assume one phase of the non-ideal flows occur regions, the wide, the large zero, and the solid Y is located at Y at zeros. And we can obtain the two equations. The substitution of the first integrates the result of the first equation into the second one, and we can obtain the equations. Next. It is a correct point to descend the wall fluid energies. Now we apply according the genius generating theories. Genius is Nobel presence in physics in his and the wall fluid energies can be expanded into the Paul series. In press workers, many researches takes the near form of the wall fluid energies, and then according the wetting boundary conditions can be presented as these ones, where A1 is related to the dimension of wetting potentials. We can see that from these equations, we can find that in exist unphysical laws films on a solid surface in a place like wetting boundary conditions. To overcome this unphysical phenomena, we use the cubical wall fluid energies which can be taken the following forms, and then a cube weighting bound equation can be derived. Here the parameter B1 can be obtained and can be obtained as follows. According to the youngest equations, we can obtain the certifications between the liquid and solid and liquid and the gas and liquid. And then according to the youngest equations, one can ultimately obtain the cube weighting bound equation for the two phases in contact with solids. As the marker is that in all the weighting boundary equations is that there's no existence of the spread films on a solid surface. Now from another equation, we can find that another viewpoint of the geometrical relations. Professor Ding has professed another weighting boundary equations. We can see that these two weighting equation boundary conditions that are different, behave different but they can actually the mathematical equivalent. But for the applications, they maybe have different difference for a given counter angles. Next. Now we to use the test C-flow test to the mode test. The first one is the job spreading on the solid surface. We can see the solid A is the surface energy weighting the boundary condition, and the case B is the result of the geometric equation. And we simulation consider the counter angle arranged from the 13 and to the large one as 30. Next, this is the result. Next, we can give a comparison of the surface energies and the geometrical weighting scales in practical counter angles. We can see that the scale A is the more stable than the scale B, such that the surface energy scale can be more stable than the geometric scales in a wider region of the counter angle, especially for the very long and the counter angle and or very large counter angles. Next. We can also, the second test is the job impact on weighting surface. We can also compare the results with the experiment by the Dong. Now we can the figure A is the result of the surface energy scales, and the figure B is the result of the geometric scales, and the figure C is the experiment data. And for this the matter of the counter angle and counter angle is not large, also is not small. So we can see that the two scale results of the two weightings boundary conditions agree well with each other, and also agree well with the experiment data. Next. For the second case, for the case of the 31, we can see the same conclusions. Next. Also, we give the computer the spring, the diameter, and the spring lattice, and then we can see the result by the two scales also agreed well with the experiment data. Next. Now we introduce some applications of the developed Boltzmann models. The first application is the turbulent relative instability. As we all know, relative instability can be widely found in many applications such as the oil recovery, the daily life, the coolness cloud, and the RCF. Let's have many research on these topics. It can be dated back to really in the 19th century. As with the invitations on this field, we can find that the theoretical and experimental studies has limited. They are focused on the early and middle stages of the stabilities. And then as for also some numerical researches, most of numerical research are just simulation, in this case, to the volatile developed code. And also in the numerical research, we can find that the most are limited to the early stages, and consider the real number is relatively is very small. In summary, we can see that the descriptions on the later time related Taylor distribution is still leaky. Now we use the Boltzmann models to simulation this complex problem. We can see next. We first to validate our code by simulation the case with the real number was 10 hundreds and odd numbers. At this case, we compare the result with the experiment. We can find that our results agree very well with the experiment. Also for the bubbles and spring amplitudes. Next. Now we use the different models to simulation the two dimensions related instabilities. We can present the result of the interface patterns of the retail instability with different real numbers. The case A, the real number is very large, and we can see that the interface evolution is very complex, especially at the late times. But it is amazing that the interface can still we maintain the existence of the systems on the middle lines. And with the decrease of the real numbers, we can see that the complexity of the interface structures is weakened. And especially for a very small real numbers for about 10, we can find that the speed is only fall down freely. And the interface cannot roll up. Next. We can also calculate is the speed and the bubble amplitudes, and we present the results. And as we can actually find that from these two pictures, that yes, we can find that increasing the real numbers, the promote the growth of the speck and the bubbles. However, when the trend cannot last continuously, when the real number is very largest, the effect of the real number become unimportant. As we can see from these figures, the results of the real number 10,000 and 100,000 can be agreed very well, and this can be to confirmed by the theory analysis. As the growth of the speckles can be demanded by the two forces. The first one is the force dissipative force, and the second is the galactic force, galactic force. And we can see here the epsilon is represent the energy dissipating rates and can be explained as its equations. So we can from this analysis we can see that for a very large real numbers the mu is very small, and so that the fast dissipative force is very small. So continue to increase in real numbers, and this force can be negative compared with the greater force. So we can conclude that our simulation results conform to the theory and analysis. Next. Then we also to measure the spec and last. We also measure the spec and the bubble growth rate, fairness awarded water numbers. We can find a conclusion is that for very small water numbers, the difference between the spread and the bubble growth rate is very small, implying the symmetric of the growth of the spread and the bubble. And for increase for larger water numbers, the spread growth rate is is larger than the bubble growth rate. Also, the spread growth rate is increased with odd numbers, while the bubble growth rate does not change much with the odd numbers, which is applied to a very about a constant values of 0.02. Next. Now we also simulation the 3 dimensions related instabilities, and we can find the same conclusions. We can find for a larger real numbers, the complex, the interface is very complex. Also, we can see very many noise of the structure, many noise, and also the interface can take up the break up, can take on the break up behaviors at the later time of later time stages. And for a small real numbers, we cannot see the break up of interface, and the speed also fall down freely. Next. The second applications is that we is used to simulation the macro geodynamics. Is a sharing of the macro jobs. I think we first compute the result with experiment. This the experiment data is taken from the PIL. We can find that our simulation results agree well with the experiment in general. Next, we can also compare our phase field Boltzmann simulation with the other Boltzmann models. We can, in the 2 cases, the Kepler number is the 0.35 and the Kepler number is the 0.4. We can see that the dynamic of a job agree with the results of the other multiphase Boltzmann models. That's the. Now we also investigate the effect of the Kepler numbers. For smaller Kepler numbers, we can see that the job can reach a steady sharp, and we can measure the Taylor parameter, and the research results it can be seen that agreed with the analytical solutions, but can be more accurate than some others numeric methods like VF, like level set simulations. Next. Also, we simulation the case with a very large capillary numbers of capillary. We can find that at a middle capillary numbers, the job can break up into 2 parts, and for a middle capillary numbers, the job can be into 3 parts, and very high capillary numbers, the job can break up in multi sub jobs. Next. We also investigate the effect of the real numbers for smaller real numbers. Now we can find that the job can break up into several sub jobs, and with the increase of the real numbers, more numbers of the sub jobs can be practiced in the systems. This is agree well with our resource, our analysis. Next. That's all. This is the talk among presentations. Thank you for your attention. And obviously the presenter a short move about the Boltzmann method simulations of the flows across the airplanes. Thank you all. Sorry for my delay. Also, my English is not very good, so you can contact me with the other manners. Thank you.
Okay, thank you, Dr. Liang, for the wonderful talk. So then we go to the Q&A time. So if our audience, if you have a question to Dr. Liang, and you can unmute yourself and ask your question directly. So Dr. Liang, I have a question about your high Reynolds number simulation, about the Rennie-Taylor instability. Maybe I can go to the slides. I want to ask a question is this one. For example, for the case 1, you simulate the Rennie-Taylor instability for Reynolds number is 10,000. Do you need any turbulence model to describe the Reynolds stress in this flow problem, or you just use do not introduce any turbulence model in this case? Yeah, the Reynolds number in this case is pretty high, right?
No, we have not used the turbulent models. This is the directed numeric simulation, DNS simulation.
Yeah.
DNS.
So okay, then you have to
without use the tunable models.
Okay. So you use very, very small size to capture all the details of the small scale flow, right?
Maybe you are very good questions. Maybe we can. Maybe this we can use if we increase the, as we all know, we want to simulation the late time staging of the later instability, and the height of the sun of the mesh should be very long, and such that so that the computer cost is very large. So if we increase the mesh, increase the number of the mesh number of in the X locations. So yeah. Of course we in our next work we need to increase give a high real solution simulations of this problem.
Okay. Okay. So any question from our audience? Okay. Okay. If not other questions, maybe I can ask another question for me. And I noticed that you do the dropnet simulation. Actually, the density ratio is extremely high. I noticed when you there's a slide you plot the density profile. It's very sharp. I'm wondering if you use any strategy to improve the computational efficiency, or you just use uniform size of the mesh. If you see here, actually the interface of the liquid and gas is extremely large. And I'm wondering, do you use any multi-grid or ununiform grid to capture the details at the interface, or you just use a uniform mesh?
No. Usually this one is a uniform mesh. A lot of non-uniform, without the use of non-uniform mesh. Of course, if we can use the non-uniform meshes, especially at the interface, we can use much more the meshes. The results of can be improved. Accuracy of them can be improved, in my opinions.
Yeah, but if you do not use ununiform mesh, then the computational cost will be extremely high because the interface is very sharp, right?
Yes, it's very sharp at the interface. It is sharp. This case is very benchmark problem. Static jobs. Now for very complex problems, maybe the non-unique meshes can be used, and we can obtain the improve the results.
This is just for static dropping.
This question is very simple, so we do not use technology.
So basically, it's just for static droplet. If the droplet is moving, I think he will have some problems.
So you need to use some interface tracking method so that your mesh can track the interface, right?
In a physical model, I don't think so. But I mean, for this case, it's just a static droplet, so it's not so difficult to capture the interface. But if the droplet is moving, you will have some problems of the numerical instability.
Okay, makes sense. So any other question from our audience? Okay, if not, then we will stop here today. Thank you very much for Dr. Liang for the wonderful seminar, and I enjoy a lot of different applications. Okay.
Second, 郑丽 profit 郑丽